So here we look at the derivatives of logarithmic functions, and we know that a logarithmic function is dependent on its base. So important thing about logarithmic functions, let me just say that base is b. So we write a logarithmic function as log base b x. In other words, or in another manner, we could write it as y equals log base b of x. Now, if I exponentiate on both sides, using the base, b raised y would equal to b raised log b x. And there is a video on the properties of logarithms that I posted. So b and log base b, they will just sort of disappear. They are inverses of each other. And we would simply have b raised y equals x. So those two are related. They are equivalent expressions. So one is in the exponential form, the other is in the logarithmic form. Some of the things that we need to know about logarithms, again, there is a video that contains properties of logarithms and how you can manipulate logarithms, but I would reiterate here, when we say a natural logarithm, we imply that the base b is e, the number 2.7182. And we denote the corresponding logarithm as ln of x. If the base is 10, we simply write the corresponding logarithm as log of x. For all other bases, we specify the base clearly. In other words, log base b of x. The value of b could be 2, 3, 7, 100. It doesn't matter. Key properties. The logarithm for any base of 1 is always 0. The logarithm of x for any base plus the logarithm of y is equal to the logarithm of x times y. Logarithm of x, the log of y, or minus the log of y for any base, is simply the log of x over y. Log of x raised m, where m is some number, we could simply write it as m times log of x. Keep in mind these properties are quite important. Oftentimes when we use the property, then when we use one of these properties, the problem would actually get simplified. So I strongly urge you that you look at these properties and understand these properties and know when to use them, because a problem can be really simplified if we understand and apply these properties, or one of these properties, properly. And lastly, we could write a logarithm of some random base in terms of the natural logarithm. And oftentimes in mathematics, we try to go for the natural logarithm. So we tend to write everything in terms of the logarithmic base, or the natural base, I'm sorry. So another property is log base b of b is simply 1, always. Now, what is the consequence of this? So recall I wrote log base e of x. If the base is e, I would simply write it as ln of x. Now, using property e, which is right over here, if I replace b by e, I would end up getting log base e of x equals ln of x over ln of e. If you use a calculator, you will find ln of e is just 1. And we would end up getting ln of x. So you could sort of understand why the property b would be quite useful. And I'm going to show how we could find or make use of it to find the derivative. So we want to find the derivative of log base b of x. Keep in mind, b is a number. So I'm going to put a note here. The derivative of ln of x is simply 1 over x. In general, the derivative of y equals ln of absolute value of x is 1 over x. When, or for all values of x, but x cannot equal 0. Sorry. What do I mean by that? So I could rewrite absolute value as so for y equals ln of absolute value of x, I could rewrite as a piecewise function, because I can't have x equal to 0, so I have a piece defined for x greater than 0 and a piece defined for x less than 0. So since the derivative is 1 over x for ln, we would end up having 1 over x for the piece x greater than 0, and for 1 over x for x less than 0 also. Now, how do we go about getting that 1 over x if the base is not e? So I'm going to show you two different approaches. So the easy approach, so approach 1, consider y equals log base b of x, and we want to find the derivative, so dy over dx, simply d over dx of log base b of x. But we know from one of the properties for any base, I could write the logarithm as ln of x over ln of b. If we go back, I used property E from above. Ln of b is a constant because b is a constant, so I could pull that out. And then I have d over dx, ln of x, which would simply give us 1 over ln of b times 1 over x. So the derivative of log base b of x is x ln of b. That's approach 1. Approach 2 is interesting in the sense it is going to use implicit differentiation. So consider y equals log base b of x, and I'm going to use one of the properties I had used earlier right here. I'm going to exponentiate on both sides using b. And I will have b raised y equals b raised log base b of x. Those two would go away, and I'd have b raised y equals x. I'm going to take the derivative, but now this is implicitly dependent on y. If you recall implicit differentiation, that is a function of y. So how do we take the derivative? We are going to treat the y as x, and if that is the case, the derivative of b raised y is simply b raised y, but then we've got to multiply by the derivative of y itself. So y prime, it would be the derivative of y. And on the right-hand side, we have the derivative of x, which is 1. Give me 1 second here. Now, I am going to plug in what log base b, plug in y. So before I do that, I'm going to write it as 1 over b raised y, which should give me 1 over b raised log base b of x. And that is nothing but 1 over, the b and log base b would go away, and I would have x. So you may wonder, well, what happened to that ln of b? Now that goes back to the derivative at this step right here. So when I wrote the derivative, I wrote it as b raised y times y prime, but that would only hold true if we have a natural logarithm. And clearly we do not have a natural logarithm. We have a logarithm of a different base that is not equal to e. So when we take the derivative, since it is not equal to e, we have to multiply it by ln of b. So that's the thing that we missed out, and that is the reason we are missing that ln of b. So I have ln of b here, and ln of b is a constant, so I could divide that ln of b we will have ln of b y prime equals 1 over x, which would imply y prime equals 1 over x times ln of b. I wanted to demonstrate how important this term is. If the base were, which is why I kind of went back and inserted that natural logarithm of b, if that b were to be e, the base e, then ln and e would get cancelled, and we don't have to specify that. But if it is any other base, you have to multiply it by ln of b. It is crucial. So no matter which approach you take, the answer is simply 1 over x times ln of b. So a quick sanity check here. I mentioned the derivative of ln of x is 1 over x. So does that work if I plug it in this formula? So we know ln of x is the same as saying log base e of x. So let's go ahead and plug it in the formula that we derived using the two approaches. So I would have y prime equals 1 over x times ln of e, but we know ln of e is log base e of e, and we know log base of log b for any base b is 1 from here. So we will have x times 1, which would give us 1 over x. And that is the derivative. Okay. So we want to find the derivative of f of x, which is ln of x plus log of x. Now, log of x is not of the natural base. The base is 10. So we have to write it as log base 10 of x. So the b in this case is 10. The derivative of ln of x is simply 1 over x. But the derivative for any other base is 1 over x multiplied by the natural logarithm of the other base, which is 10. So the base plays a very important role when we take the derivative of logarithm. So be very careful. So as a different example, for instance, suppose we wanted to find the derivative excuse me. We want to find the derivative of log base 2 of x plus log base 4 of x. We know the derivative of a logarithm is simply 1 over x, but the base here is 2, so I'm going to multiply by ln of 2. Same, the base here is 4, so I'm going to multiply by ln of 4. And what do we have in common? We have 1 over x in common. And if I pull that out, I have 1 over ln of 2 plus 1 over ln of 4. You may say, well, I could leave the answer as is, but you could actually simplify it further. I'm going to go one step further so that you get accustomed to the properties of logarithm. So I am going to take a common denominator, which is ln of 2 times ln of 4, multiply and divide by ln of 4 for the first term, multiply and divide by ln of 2, I have a common denominator, so I can combine the numerators. And ln of 4 plus ln of 2, if we use property b here, would equal to ln of 4 multiplied by 2 divided by ln of 2 times ln of 4. But ln of 2 times 4 is simply ln of 8. And now you may say, that looks kind of simplified. Should I just stop there? Well, if you think about it, ln of 8 is ln 2 raised 3, because 2 cubed is 8. Bring the 3 to the front, so I'm going to use property D now. So 3 is going to come to the front. The ln of 2's will get cancelled. And the answer is 3 over x times ln of 4. And that is the final answer. Now, what looked like a giant expression when we first found the derivative right here simplified to that nice little expression. And that is possible because we know the properties of derivatives. excuse me, I didn't mean to say properties of derivatives. We know the properties of logarithms. So now we move on to this function of a function, and we all know what we should do when we have function of a function. So the hint here is to use chain rule. We are going to treat ln of x as just x. If that is the case, what is the derivative of cosine x? It's negative sine x. So we would have negative sine ln of x. But we multiply it by the derivative of the function that's inside. What is the derivative of ln of x? It is 1 over x. So the derivative is negative sine ln of x divided by x. In this problem, the independent variable is t, the dependent variable is y. So again, we have a function within a function, so ln, and within ln we have another function in terms of the independent variable, so we have to use chain rule again. If I treat that t squared plus 1 as t, then the derivative of ln of t is simply 1 over whatever we have. So that would be t squared plus 1. But then we realize that it is not t, rather it is t squared plus 1. So we multiply by its derivative. The derivative of t squared is 2t, and the derivative of 1 is 0. So here it is dy over dt. So we would get 2t divided by t squared plus 1. So this is a problem of extreme importance. Now, one may say the immediate thought would be, oh, we have a function within a function, just like the previous problem. In the previous problem, t squared plus 1 was within ln, and we use chain rule. And you may say, well, let me do the same thing. Sine x plus 1 divided by sine x minus 1 is inside ln. So using chain rule, we could find the answer. That might be a thought that will come to your mind. But even though that is a good approach, we don't want to do that approach, because if we did that, we have to use product rule. So I'm going to show you both approaches, and you can be the judge and determine which is better. One is going to use the properties of logarithm, the other is going to use chain rule. And you would see that if we use the properties of logarithms properly, then we could save a lot of time in finding the derivative. So here we go. So approach 1 using chain rule. So g prime is dg over dx, I'm going to treat whatever that is inside the logarithm as x. If that is the case, we would simply have 1 over sine x plus 1 over sine x minus 1 multiplied by the derivative of sine x plus 1 divided by sine x minus 1. Now I could flip and multiply and write the first term as sine x minus 1 divided by sine x plus 1. And we have to take the derivative of sine x plus 1 over sine x minus 1. Now this is a function with u over v. So we need to use quotient rule. U is sine x plus 1. V is sine x minus 1. U prime is cosine x plus 0, which is cosine x. V prime, sine x minus 1, which is cosine x. Derivative of negative 1 is 0. If I use quotient rule, I would get v u prime minus u v prime divided by v squared. Which would give me sine x minus 1 multiplied by cosine x minus u is sine x plus 1 multiplied by cosine x again divided by v squared, and that is sine x minus 1 squared. Distribute and simplify, we would get sine x minus sine x cosine x minus cosine x minus sine x cosine x minus cosine x divided by sine x minus 1 squared. Those two terms would go away. We will have negative 2 cosine x divided by sine x minus 1 squared. We're not done yet. Now that is just the derivative part, which is right here. We have to find g prime. So let's go ahead and plug it back in. G prime would be equal to sine x minus 1 multiplied by sine x plus, divided by sine x plus 1 times minus 2 cosine x divided by sine x minus 1 squared. That term and that term would get cancelled, and g prime would be negative 2 cosine x divided by sine x plus 1 times sine x minus 1. And that is the final answer. We did all that work and we got to g prime. And here is approach 2. Approach 2 is going to make use of the properties of logarithmic functions. So what do we have here? ln of sine x plus 1 divided by sine x minus 1. Let's go back to the properties. Look at the property that is right over here. X over y, I could split it up and write it as the numerator logarithm minus the denominator logarithm. So g is simply ln sine x plus 1 minus ln sine x minus 1. Now we have to use chain rule here again because we have function within a function. So g prime would be 1 over sine x plus 1 multiplied by the derivative of sine x plus 1. Derivative of sine x is cosine x. The derivative of 1 is 0. So cosine x plus 0 is cosine x. So I would leave it as is. Minus, same thing here, 1 over sine x minus 1 multiplied by the derivative of sine x is cosine x. Derivative of negative 1 is 0. Cosine x minus 0 is cosine x. So that would give me cosine x over sine x plus 1 minus cosine x over sine x minus 1. Cosine x is in common. And you'd say, oh, that answer doesn't look anything like the answer right here. And I'm going to tell you that they are one and the same. So I'm going to take a common denominator. So multiply and divide by sine x minus 1. And in the second term, multiply and divide by sine x plus 1. Now we have a common denominator, and that common denominator is sine x plus 1 multiplied by sine x minus 1. So I simply combine the numerators, which is sine x minus 1 minus sine x plus 1. Distribute and simplify. Cosine x sine x minus 1 minus sine x minus 1 divided by sine x plus 1 times sine x minus 1. The signs would go away. We have minus 1 and minus 1. We get minus 2. So negative 2 cosine x divided by sine x plus 1 multiplied by sine x minus 1. Exact same answer. I personally think that the second approach had fewer steps and we were able to get the correct answer. If you look at approach 1, we had to do chain rule, then we had to do quotient rule, we had to simplify, and finally we got the answer. But with approach 2, we used the property of logarithms, used chain rule, and the rest of it was simply algebra. Before we move on, again, this is a matter of choice in the previous problem. Some may prefer approach 1, some may prefer approach 2. It is a matter of choice. You pick the one that you are comfortable with. I personally like approach 2. I think approach 2 is easier. and you can implement it properly if you understand the properties of logarithms well. So this problem looks like a very complicated problem, but by all means it is not. First off, we have log base 2 of 2 raised sine or square root of sine x squared. The log base 2 and 2 would go away. Let me not do it there. Because they are inverses of each other. As I mentioned earlier today, you're also welcome to look at one of the videos on logarithmic functions. And this particular property is summarized in that video as well. So that would go away, and we would simply have y equals square root of sine x squared. Clearly, square root of something is a function, and we have function within a function. So y prime, we have to treat whatever that is inside the square root as x. So what is the derivative of square root of x? Recall, the derivative of square root of x is 1 over 2 square root of x. If that is the case, I would have 1 over 2 square root of sine x squared, but we simply don't have x, rather we have sine x squared, so we have to multiply it by the derivative of sine x squared. And once again, we have a function within a function. X squared is a function. So if I treat that x squared as x, the derivative of sine x is cosine x. So I would simply have the derivative of sine x squared, which is cosine x squared, but multiplied by the derivative of x squared. So we would have 1 over 2 times square root of sine x squared multiplied by cosine x squared. Derivative of x squared is 2x. The 2 here and the 2 there would get cancelled. We have x cosine x squared divided by square root of sine x squared. And that would be the first derivative of y. So a common mistake is when you see a plus sign here. I have seen students split up that logarithm. You cannot do that. If you have logarithm of x plus the logarithm of y, we can write it as ln of x times y. But we can't write ln of, say, a plus b as ln of a plus ln of b. This is incorrect. So don't make that mistake. So how do we find the derivative? We have a function within a function. So we're going to treat the shaded part that is inside the logarithm as x. So the derivative would be 1 over e raised x plus x squared e raised negative x, because the derivative of ln of x is 1 over x. So whatever I have highlighted there comes over here. But we have to multiply by its derivative, since it's not just x, rather a function of x. So we have e raised x plus x squared e raised negative x. So we have to find that derivative. I'll do that separately. Distribute the derivative. The derivative of e raised x is e raised x. The second part, we have x squared multiplied by e raised negative x. So we have to use product rule. Call that u, v. So that derivative would be u v prime plus v u prime. Let's go ahead and compute u prime and v prime. U is x squared, v is e raised negative x, u prime would be 2x, and v prime is negative e raised negative x. So we would have e raised x plus u v prime minus x squared e raised negative x, v u prime plus e raised negative x times 2x, which would give us e raised x. We have an x in common, we have e raised negative x in common. If you pull that out, we have x e raised negative x minus x plus 1. Oh, sorry, plus 2. So that is not the answer, that is just the derivative for that part. So we have to get to the final answer, which is y prime. Y prime is 1 over e raised x plus x squared e raised negative x multiplied by e raised x plus x e raised negative x multiplied by 2 minus x. Okay, that is the first derivative. Now we have to find the second derivative. Which would be the derivative of the first derivative. So that is u and that is v. V is e raised x plus x squared e raised negative x. U prime. So u prime would equal derivative of e raised x is e raised x plus that. That is a product of two functions, so we have to use product rule. So I'm just going to call that as m and that as n. So we are going to fill that in. So m times n prime plus n times m prime. What is m? M is x e raised minus 2x. N is 2 minus x. This would mean n prime is derivative of 2, which is 0. Derivative of negative x is negative 1. That was easy, but the derivative of m requires product rule again. So I am going to call that as S and that as T. So we have S T prime plus T S prime, and that would give us M prime. So what is S? S is X, T is e raised negative 2x, S prime is 1, T prime is e raised negative 2x multiplied by negative 2. So we have found M prime. M prime is x times e raised negative 2x times negative 2, S T prime plus T multiplied by S prime, which is 1. So we have negative 2x e raised negative 2x plus e raised negative 2x. So now we have M prime, N prime, M, N. So we could plug all of those in there. I should have space. So M N prime plus N M prime would equal to M is x e raised negative 2x multiplied by N prime is simply negative 1, plus N is 2 minus x, multiplied by M prime, which is negative 2x e raised negative 2x, plus e raised negative 2x. Let's see if we can simplify x e raised negative 2x with the negative in the front. I have a e raised negative 2x in common, so I'm going to pull that out from the second term, which would give me negative 2x plus 1. Now I have e raised negative 2x in common here, as well as there. If I pull that out, I would have negative x plus 2 minus x times negative 2x plus 1. If I FOIL and simplify, I would get minus x minus 4x squared plus 2 plus 2x minus x. So, negative x, negative 4x squared plus 2 plus x. Those two would go away. I have the 2 in common. If I pull that out, 2 e raised negative 2x multiplied by negative x squared plus 1. That is u prime. So we found u prime. U prime is the e raised x plus the product rule that we did, and we got the second part, mn prime plus nm prime. So I'm going to throw that in there. Now, we already did the work for v. So v prime, we know. What is v prime? Well, v prime is the derivative of that, which is right over here. So From the first derivative, we know v prime is simply e raised x plus x e raised x times 2 minus x. Right over there. So using the quotient rule, y double prime is v u prime minus u v prime divided by v squared. V is e raised x plus x squared e raised negative x. U prime e raised x plus 2 e raised negative 2x times 1 minus x squared minus u, which is e raised x plus e raised negative 2x times x times 2 minus x multiplied by v prime e raised x plus x e raised x times 2 minus x, and the entire thing would be divided by v squared, and that would be e raised x plus x squared e raised negative x squared. That is a lot of work. We can still simplify this algebraically, and that would take a lot of time. Is there a different way to approach this problem? Let me see if I can add a page here. Odd. Add page. Okay. I'm going to put it in the very last page. So the problem that we had here is this: y equals ln e raised x plus x squared e raised minus x. We had to find the second derivative. We did all of this. Extremely lengthy expression and seems quite painful to simplify. So I'm going to use a different approach. Well, this is, kind of tricks that we use to make things easier for ourselves. So what I'm going to do now is I'm going to exponentiate on both sides. So e raised y would be equal to e raised ln e raised x plus x squared e raised negative x. Those two would simply go away, and we have e raised y is equal to e raised x plus x squared e raised negative x. Let's take the derivative. Now that becomes an implicit equation, because we have a function of y. So To find the first derivative, I have to take the derivative implicitly, treat that y like x. We have e raised y multiplied by the derivative of that. We get y prime. Have to take the derivative on both sides. And the base is e, so we multiply by ln of e, which is simply 1. On the right-hand side, we have e raised x plus the derivative of x squared e raised negative x. Well, product rule, we'll call that u and v. U is x squared, v is e raised negative x. U prime is 2x, v prime is negative e raised negative x. So if I use the product rule, I have u, v prime, plus v, u prime. We have an x in common, e raised x in common. If I pull that out, I end up getting that. So which would mean y prime is equal to e raised x plus x e raised negative x multiplied by 2 minus x divided by e raised y. But I know e raised y is given in the problem. So I'm going to plug that back in. The e and the ln would go away, and we would simply have e raised x plus e raised x, x times e raised negative x times 2 minus x over e raised x plus x squared e raised negative x. That should look familiar. Let's go back. That's exactly what we had here for the first derivative. So we did all that to get the first derivative, and I simply changed it to an implicit equation, reverted it back by substituting y, and I got the answer right away. I personally think that this approach is more efficient. So how do we find the second derivative? Now, all this mess that we made over here and that giant lengthy expression happened because I went and did product rule multiple times, a quotient rule, and I have several e terms. Let's take the implicit differentiation approach. So I'm not going to start here. If I started here, I'm just repeating the same mistake again. So what I'm going to do is go to the step prior to that. From above, we know e raised y times y prime equals, that. Now I want to take the derivative on both sides. So left hand side we have to use product rule because we have e raised y times y prime. So derivative of e raised y is simply e raised y times y prime. So I will have u v. So the derivative is u v prime. Derivative of y prime is y double prime plus y prime. Derivative of e raised y is e raised y times y prime. Implicit differentiation. And on this side, we have derivative of e raised x is simply e raised x. We already have the derivative of that term. We derived it painstakingly. X e raised x Unfortunately, we didn't. Okay, no big deal. So e raised x, and I have u v product rule, u v product rule again. So for the first one, I have u times v prime negative e raised negative x, v times u prime derivative of 2x is 2, minus u is x squared, u times derivative of e raised negative x is negative e raised x, plus v e raised negative x, derivative of x squared is 2x. Shouldn't be there. Taking the derivative, so e raised x plus 2 or minus 2x e raised negative x plus 2 e raised negative x, distribute the negative, plus x squared e raised negative x minus 2x e raised negative x. Let's say if we could combine terms, we have e raised x plus negative 2x e raised negative x, negative 2x e raised negative x would be negative 4x e raised negative x. So we would have 2 e raised negative x plus x squared e raised negative x minus 4x e raised negative x. We have e raised negative x in common. I'm going to pull that out and write it as x squared minus 4x plus 2. And on the left hand side, I have e raised y in common. I'm going to divide by e raised y. And y prime times y prime is y prime squared. So y double prime plus y prime squared would equal e raised x plus e raised negative x multiplied by x squared minus 4x plus 2 divided by e raised y. I'm going to do what I did with the first derivative. Plug in y, which is ln of e raised x plus x squared e raised negative x. Those two would go away, and we will have e raised x plus e raised negative x x squared minus 4x plus 2 divided by e raised x plus x squared e raised negative x. And that would equal to y double prime and y prime squared. Now you don't have to plug in y prime and try to solve this again, because if you know what y prime is, I could evaluate it as a function for any given value of x. And then I could take that and plug it here in the second equation. So I can leave the second derivative as e raised x plus e raised negative x multiplied by x squared minus 4x plus 2 divided by e raised x plus x squared e raised negative x minus y prime squared. And that is implicit. And that is also an acceptable solution. The key here is it didn't save us a lot of work when it came to the second derivative, but using implicit differentiation certainly made the problem easier in finding the first derivative.